go. Question 34. Looks like a tough one. Let's see how bad it really is. In the circuit shown, all the resistors are identical and all the ammeters have negligible resistance. The reading on the ammeter A1 is 0.6 amps. What are the readings on the other ammeters? All right, so let's kind of just label this. This is 0.6 amps. And so this has a resistance R, this has a resistance R. Maybe we should just make numbers up for them. 1, I don't know. So it looks like here's a series circuit here. This is our EMF. And then we got this in parallel. So we got this sort of loop right here. Right, and so once the charges get to, say, like they leave, let's say the charges are leaving this negative terminal, right? They're getting pushed, the electrons in this wire are getting pushed by the negative terminal of this battery. And once they get here, some of them go that way and some of them go that way. We know that 0.6 amps go through both of these because that reading is given to us. And so 0.6 amps is like everywhere in this part of the circuit. Everywhere in this series circuit, there's 0.6 amps. But as soon as it gets to here, this node, some of those 0.6 amps go that way, some go through here, right? And so we know that there's, we don't know what the current is in A2. In other words, A2 isn't the same as 0.6. Obviously, it's got to be one of these values. So it's greater than 0.6, right? Because it's kind of like charges are going into it from this point, right? So you got 0.6 amps coming in here, and you got some current flowing in this way, okay, to give us more than that A2, all right? A3 and A4 down here, what's going on there? So it's like the charges, the more than 0.6 amps that were in this branch, okay, 0.6 went that way, some of them went this way, we don't know how many. And then when they get here, it's like they go up through there, and then they go down through here. Okay, so these amps that got into this node are going up through here, going through here, meeting back up. Okay, so we got this loop right here, right? So this is a parallel sort of loop. We got sort of this loop right here, this loop right here, and then you got this loop right here, right? That's a third loop. And so now we have to consider like how much resistance there is in each one of these. And this is, once we kind of very familiar with all of the, circuits, this is how it goes. You can really look at this and go, okay, I've got 3 sort of parallel branches, and there's like 2 R's here. There's only 1 resistor in this loop, right? So like there's only 1. So that's why there's the most current in this one, because it's resisting the flow of charge the least. This one resists the flow of charge the most, right? Because it looks like in this loop, there's 1, 2, there's these 3 resistors, right? And then it still is kind of going through this. So if 2 resistors resist the flow of charge to give us 0.6 amps, then 1, on the value of it, and then here we got 1, 2, 3, 4. So could we just say, since this loop is resisting the flow of charge half as much as this loop with 4 resistors in it, then twice the current will be in here? Could we say that? Now let's be careful here, because is it 3 or is it 4 resistors? This node have a junction, so there's this loop here, and there's this loop, they meet back here. Yeah, so we really got to look at the loop with EMF. Like, here's the EMF source right here, so like there's the loop. Here's the loop, and then here's the outside loop. We really got to kind of look at it like this. Okay, like there's a parallel circuit with this circuit, and there's this one here. So there's 3 circuits in parallel, but this circuit right here, I'm sorry, this resistor right here isn't really part of this outside loop, right? There's just 1, 2, 3. So we could really say this loop resists the flow half as much as this one. And so twice the current should be flowing through it, 1.2. But that's not an answer, is it? Well, A3, 1.2. So if we said there's 1.2 amps going through here, if this is 1.2 amps and this is 0.6 amps, then we would say, well, this would be 1.8. Let's see, then that's this answer. And so already we sort of made a mistake. So, well, that can't be. So this loop is resisting the flow of charge half as much, but it's also getting sort of the charge, from this EMF. Let's think here. This one has 2 resistors. This one has 1. 0.6, then this would be 1.2. Well, you'd say 1.2 amps flows through here. And that would be 1.8. If you said, well, this is 1.8, then that would mean 0.6 go that way, 1.2 go that way. If you have 1.2 going here, but not all of them can go through this, right? In other words, if you just say, well, maybe that's right. Maybe the reading in this one is 1.8, and then you can kind of use Kirchhoff's law to, again, when there's different ways to sort of approach this, and we're just doing sort of I'm kind of stuck and I'm getting myself out of trouble here, just sort of throwing all the physics I can at it. I'm not solving this from first principles, doing it, like an equation with 2, 1 to 3 resistors. And maybe just look at that. So like what numbers are in that ratio, right? And that may be a very elegant path sort of to the solution there. If we said that the reading in this ammeter A2 is 1.8, then there's 0.6 going this way, then there is 1.2 right here, but then those 1.2 amps, not all of them would go through this. And so A3 wouldn't be 1.2. It might only be 0.9, right? Because 0.9 amps go through that. That would mean the other 0.3 amps are going this way. 0.3 amps, because there's 3 resistors, only 1 resistor means that 3 times the charge is going to flow through it. There's your ratio. So 0.3, 0.9 to 0.6. And so the reading in ammeter A4 might be 0.3, right? If the reading in ammeter A3 is 0.9, the reading in ammeter A2 would be 1.8. And that would be 3 times the current of 0.6. But wait a minute. Should this be 3 times this? This is 2 resistors. This one's only 1. So we kind of said, oh, look, this kind of works here. But does it really work when we consider what the resistors are actually doing? 0.3, 0.9 is good, but 0.9 compared to 0.6, so I'm really leaning towards choice C here. But let's take a moment to just clear all that out. Think through it again. If you're completely stuck and you said, I just don't know, I'm just gonna try some values out here, and you consider choice A, and you say, if there's 0.1 amps here, and there is flow this way, not this like this, and we have this one going sort of that. So you have the 0.1 plus, you'd say A3 would have a reading of 0.3, 0.1, and then this would be 1, and this one would be 0.6. Does that even work? You say 0.3 plus 0.6 is not 1. And you could immediately disprove that that would not be right just by using Kirchhoff's first law. And so sometimes it might be good to say, well, let me just use like a familiar law like Kirchhoff's first law to see if I can eliminate obviously incorrect answers. In order for this to work, the 0.3 amps, okay, that are in A3, okay, wait, plus the 0.1 amps here, that actually would be 0.4. Okay, wait, so that does work. My bad. So we can't do that. Maybe they'll all sort of work that way. 0.1, so if we said, what about, so that one does actually work out. Would this work if you had 0.2, 0.6, A3, and if you had 1.4 here, then you'd have your 0.6 plus your 0.2, so this would be 0.8. 0.8 plus 0.6 is 1.4. So this one checks out too. This one, I think we said we know works because we have our 0.3 here. We have your 0.9 there. You have your 1.8 here. So you're saying, does the 0.9 plus 0.3, the 1.2 plus the 0.6 add up to 1.8? And it does. And then this one, you've got 0.4 through this one, plus 1.2 through here. That would mean you've got 1.6 right here. So the 0.6, and then this one would have to show a reading of 0.4 plus 1.2, 1.2, so that would be 1.6. 1.6 plus 0.6 is indeed 2.2. So they've given you 4 possibilities that all work in terms of Kirchhoff's first law. In other words, the sum of the currents sort of works out to give you, like they're all meeting back up through here where they have to because this is where the EMF is, right? So the sum of the EMFs have to equal the sum of the PDs. So now we have to sort of think through it, like that. Did we get it? Any one of these would sort of work to just say, well, Kirchhoff's first law kind of works. 3 resistors to 1 resistor to 2 resistors. Now this is the ratio of resistors, 2 to 1 to 3. Right? So the ratio of the currents, okay, so this resists the flow of charge the most, so it should be the lowest. And I think that, again, we kind of know that they're all in sort of that proportion. The thing that we know here is that A2 is the sum of A1 plus A3 plus A4. That's what we know. So Kirchhoff's first law is really telling us that A2 is the branch where all of the currents converge. The current in A1 goes here. This current is already the sum of A3 and A4, right? A3 and A4 converge at this node, so they're going through here. So A3 plus A4 is added into A1 to give us A2. So A2 is the sum of all of these here. All right, so we know that's true. This one has to equal the sum of 0.6 plus, these 2. And that by itself has infinitely many solutions. And we see like there's 4 of them right there. Like all 4 of these answers work with this equation. You could plug in these values for A2. Like that's what we have already kind of shown. In terms of the circuits that we've got here, okay, we've got the resistance in A1 in this loop is 2 resistors, and it's giving us a current of 0.6 amps through the 2 ohm resistor. 2 to 1 to 3, 0.6. But see, this one here isn't just going to solve for the current in this, because this is the sum of all of them. So it's a little bit more, a little bit trickier than that, huh? The goal with this, you know, dedicating all the time to thinking through it like this is that you hopefully will realize something about it. They say, oh, you know, like you deep learning only occurs when you kind of have some confusion there. And so you want to kind of say, okay, well, there's got to be another way to think about this that's going to make one of these answers sort of very, very clear that I'll convince myself, yes, that's got to be it. You know, so I feel like we're on the verge of that here. 2 to 1 to 3 is the ratio of the resistances in each of these series circuits. You just sort of say, here's a series, here's a series, here's a series. This one only has one resistor in it. So it's really, that's A3. If we think about, well, the reading in A3 compared to the reading in A4, the currents, this one has 1 compared to these 3. So that should be right. So instead of thinking about this as like this loop and what A2 is going to read, this answer, we should be thinking about that will give us this answer. If we said this ratio, you know, 2 to 1 to 3, so then what is half of 0.6? 0.3 amps. But that should be the reading in A3. And then what is, if this has 3 times the resistance here, then we'll have 1/3 the charge. And so 0.1. So at first I was leaning towards C, but now I think it might be A. Because does this idea work for these other ones? All right, so if I said, I know that the actual value of the current is 0.6, but I'm kind of thinking to myself right here that this is the ratio of resistances, and so the ratio of currents is kind of like the inverse of that, like 2 to 3, so it'd be 3 to 2. 2 to 1, so it'd be 1 to 2. In other words, this is half of that, 2 to 1, still there. Which branch has half the resistance? This one. So this ammeter would read half the resistance. I'm sorry, would have half the resistance and therefore read twice the current, because it's resisting the flow of charge half as much or half twice the current. So if this is twice the current of that, then that's 1.2. Wait a minute. How would this mean? Because the reading here is going to be less. That's just using the ratio here. If the resistance is half, the current won't be half, it will be twice. So 0.6 becomes 1. Okay. And then this is 3 times the resistance of this loop. And if this loop has a current of 1.2, and this thing is resisting the flow of charge 3 times as much, then 1/3, you know, of the current will go through, or 0.4 amps. And we already said, like, Kirchhoff's first law works to get them all sort of, this adds up to that. So we know that that's going to work for all of them. We really need to use this idea of we're given 6.6 amps here. And we just kind of know like 2 resistors in this one resistor in that one. So the reading of A3, again, A2, you have to kind of think about like the reading of this one is just the sum of all of these. And so it's kind of like this answer right here has to equal this plus 0.6. So like add these to 0.6 and you'll get these answers. So when we're considering the ratios of resistors, we're thinking, okay, well, 2 resistors in this loop for the reading in A1, 1 resistor in this loop for the reading in A3, not A2. A2 is, again, all of them. The reading in A3 will just be considering, okay, a 1 resistor loop with an ammeter right next to it, right? In other words, the charge going through this is going through that. This one is after a node where charges have met back up, and you know the current here is going to be, again, a sum of all of them. This is the sum of A1 plus A3 plus A4. And then we've got, so there we got our 1, and then here we've got our 3R. Okay. And now we're saying the voltage is the same across all of these. Okay, so V equals IR, and the voltage is the same across all of these branches. Okay, so here's a parallel branch to that one, to this outside loop, right? So we've got 3 sort of parallel loops with the voltage the same across each of them. So we're really using how the resistors are changing to give us the current. And so let's think about how current is equal to V over R, but it's like, you know, the same V, so we'll just call it 1. Let's say the voltage was 1, right? And so they're inversely related. And this is when we consider the ratio 2 to 1 to 3 for the values of the resistance. Then we say, well, then the inverse, you know, sort of currents. And so if we know that the current in this was 0.6 amps, right? That was in our 2 resistor branch of the circuit. Then because the ratio of resistances is 2 to 1, we're going to have the inverse of that for the ratio of the currents, right? And so instead of having a 2 to 1, it's going to be a, so it's going to be 2 to 1 the other way, right? So 1 to 2. So the reading in A3 should be 1.2, right? So in other words, how are we setting this up very for me? So it's kind of like I1 over I3 is equal to, you know, 2R over R, right? Because they're inversely related. So the 2R that went with A1, you know, goes down here in the denominator. And so this is kind of how you can think about setting it up, where we know that the current of this is 0.6. So it's like 0.6 over I3 equal to R over 2R. The R's cancel, and we get 0.6 over I3 equals a half. Multiply both sides by I3. And multiply both sides by 2, and then there you've really proven it. I3 equals 1.2. So there's a very mathematical way to sort of think about that, right? So we're setting up sort of like this inverse proportions. We do the same thing. You could sort of set up the other way. Like we could have set it up I3, which would be the current in, you know, that ammeter, to I1, and then it's just sort of like, okay, well, the resistor that goes with I1 goes up here in the numerator, since that's in the denominator. Again, there's inversely proportional. So it's like saying this was the 2R compared to this R, and we just kind of solved that. We plugged in the 0.6, we canceled out the R's, you know, and so I3 is just twice this, right? So plugging in values to this solves it for A3. The same thing should work over here now. Where we've got this ratio of resistances. And so if we want to set it up like I4 compared to I1, it's like the unknown compared to the thing that we do know. And now let's set it up with the inverse sort of resistance. And so the resistance in this one was 3R. The resistance in this one was 2R. And so it's not as straightforward, right? It's 2/3. And so if we plug in now I4 over 0.6, right, which is the current in A1, equals 2/3, multiply both sides by 0.6, was 2/3 of 0.6, 0.4. And so here we're solving I4 equals 0.4. All right, and so I've thought my way through it again and again. But oh yeah, C looks good, let's just try some numbers. Well, let's try some more numbers and really see does it really work. Yeah, every number works. Okay, let me confuse myself with A and sort of get it wrong here. Now A2 has to add up to all of these. It's not like we just say, oh, well, this has got to be a third of it or whatever. So A is no good. It's got to be B, right? These things, A3 plus A4 plus A1, the 0.6 plus this adds up to the 2.2, and they're in the right proportions according to how many resistors are in each one. Now here's the moment of truth. $34 choice D. Take a look. All right, there it is, 34D. Well done, everybody. Could have done it without you.